Welcome back, superstars. This video will be about the types of chemical bonds and Lewis structures. There are various types of chemical bonds: ionic, polar covalent, nonpolar covalent, and metallic. So, in one of our previous videos, we talked about forces like electronegativity, or the ability of an atom to attract electrons. Well, this is what bonds are all about: valence electrons. First, let's talk about ionic bonds, which is the picture that I have right here. Ionic bonds put together a cation, which is the Na+, and an anion, the Cl-. Ionic bonds put together a cation and an anion involving a full transfer of electrons. So, valence electrons are the most outer electrons on an atom. These are the electrons that react. These are the ones that we look at because they are the electrons that react with other electrons. They're important. They define the characteristics of any element. So, sodium has 1 valence electron. Chlorine has 7. How they bond together is that sodium gives its electron to chlorine so that chlorine can have 8 valence electrons. A rule in chemistry is that 8 valence electrons equals stable. Elements always want to be stable. They always want to have 8 valence electrons. Of course, there are exceptions, but for the most part, this is the rule. Second, we have covalent bonds. These bonds are a sharing of electrons. They don't completely transfer like sodium and chlorine did. They share. Polar covalent bonds, so fluorine here has 1, 2, 3, 4, 5, 6, 7 valence electrons. Fluorine also has 7 valence electrons. These two are covalent bonds. What they do, how they react, is that notice how they both have 7. How can they come together so that they both have 8? Because remember what I said, 8 is the magic number. They'll come together and they'll share each electron so that both of them are sharing 2. So that when you count them up, 1, 2, 3, 4, 5, 6, 7, 8, they'll each have 8 valence electrons and they'll both be stable. This is the compound F2. There are 2 different types of covalent bonds. There are polar covalent bonds and there are nonpolar covalent bonds. Nonpolar covalent bonds are when the electrons are shared equally. So, this is an example of a nonpolar covalent bond. Both of these atoms are taking the same amount of the electron as the other atom is. So this fluorine is taking 50% of it, and this fluorine is also taking 50% of it. Why? Because they have the same electronegativity. What did I say electronegativity was? Electronegativity is the ability of an atom to attract electrons. If an atom has a higher electronegativity, then it's going to attract a higher percent of the electrons than its other atom. Here's an example of such. So this is an example of a polar covalent bond, when the electrons are shared unequally between atoms. So, I don't expect anyone to know this, but hydrogen has a lower electronegativity. As compared to oxygen, meaning that oxygen is going to want more electrons. It's going to take the electrons from the hydrogen. Not completely, okay? The hydrogen still holds on to some of it, right? Think of it like this. If we're playing tug of war and I'm the oxygen and I'm a lot stronger than you are and you're the hydrogen, that's kind of how this relationship is. You guys are still holding onto the rope, but oxygen is just a lot stronger than the hydrogen. This dash is just the bond of electrons that we talked about. Another a really important fact of how to tell between ionic and covalent is that ionic bonds will always be between a nonmetal and a metal. So see here, ionic bonds will always be between a gist of what's over here and what's over here, so a nonmetal and a metal, whereas a covalent bond will be between two nonmetals. Okay, so the whole electronegativity thing is what is going on here. I know it seems confusing, but it's not. So what are electrons, right? Electrons are negative energy. They're like packets of negative energy. If the oxygen is having a stronger hold on that negative energy, which atom do you think is going to be more negative? The oxygen is going to be more negative because it's going to have more negative energy attached to it. This is what this is. These are called dipoles, right? Or partial positives. Since the oxygen is holding on to more of the electrons, it is partially negative. Partially negative because it's holding on to the electrons. Whereas since the hydrogen is kind of letting loose of the electrons, it's partially positive because it has less electrons. These arrows are just dipole arrows. They just point to the more electronegative atom. Another bond is a bond between metal. Bonds between metal. They're completely different than covalent or ionic bonds, and they're not looked at as much in AP Chem, but they're still pretty important to know. So this is called a sea of electrons. When you see copper, or when you see gold, when you see any of this, this is how their structure is. So you know how atoms are made of a proton and then a bunch of electrons around it. Well, here's what happens here. The protons are going to not really separate from the electrons, but allow the electrons to go free. They're not going to be attached to the proton like they are here. The electrons are going to be able to move freely, bouncing around each cation, or bouncing between each proton. This kind of gives metal a kind of more flexibility. It allows it to be more flexible because even if it were to move, even if this were to go sideways or go forward, the electrons would still have contact with whatever proton that it wants to be in contact with. They still have that electrostatic attraction, and so that's why metal has that better bending ability and it's malleable. So that was it for the bonds. Now we can talk about Lewis structures. Lewis structures just represent compounds with drawings, and it's really important in the fundamentals of chemistry. Here is a Lewis structure. You know how usually we have been referring to water as H2O? Well, it's easier if we can look at what H2O actually looks like and like the way that the atoms are connected. Here is the Lewis structure for water. We're going to explain this soon. So, in order to understand this, you have to understand how an individual atom looks like with its valence electrons. So, each atom has valence electrons. I explained what valence electrons were beforehand. So, like fluorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Oxygen has 6, and nitrogen has 5. You might be wondering, where do we get this information? Well, if you look on a periodic table, if I can find it, if you look on a periodic table, and you look at your group number on the top, I know it's not a very good copy, but these numbers on top of here will tell you the valence electrons for every single element in that entire group. It's very helpful. So these are the electrons that will react in a compound. Drawing them, however, is a little more difficult. Okay? I'm gonna write out the steps. So first, you should add up the amount of valence electrons of every atom in a compound. I'll do an example so that will make more sense. 2, draw the skeleton. 3, keep track of electrons used. 4, check if any element is not satisfied. So what did I say before about this? I said that 8 valence electrons means that an atom is satisfied. That is always what we want to look at. Of course, there are exceptions, but that's not something that I would like to go over as of now. We will go over that in a later episode. Okay. So here are a few examples. Let's do the Lewis structure for CH4 or methane. Okay, so first I said to add up the amount of valence electrons. You can go ahead and go on your periodic table. You can pause, but I'll take a little break so you guys can do it. So there are 4 valence electrons in carbon, and there's 1 for each hydrogen, so 1 times 4. That's 8 electrons in total for this compound. An important thing in Lewis structures is that the atoms or the elements are going to want to be as far away as possible, because you have to remember, each element has electrons surrounding it. Remember, electrons do not attract. They don't want to be near each other. They don't like each other. You can think of it as they have drama. They have beef. They do not want to be next to each other. So when you draw the skeleton, you want to draw it in a way that the elements are far from each other. And also an important note to add is that carbon is always going to be in the middle of the Lewis structure. It's never the case where carbon is on the outside. So here you would make carbon your central atom, then you would put hydrogen next to it, hydrogen, 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 and that's your skeleton. Remember that each bond is 2 electrons, as we discussed briefly before. Each bond is 2 electrons. So how many is that? 1, 2, 3, 4, 5, 6, 7, 8. Good, you used up all 8 electrons. So that is your Lewis structure for methane. We can move on to a little bit of a harder example, but something that still takes the gist, because you guys are just learning this out. I understand how it can be confusing. Let's do this compound right here. What did I say our first step was? Right, count up the amount of valence electrons. So we know that there's 4 in carbon, and if you look on your periodic table, look at the group number that's on top of chlorine. That's 7. How many chlorines are there? 4. 7 times 4, 7, 14, 21, 28. Okay, plus 4, 32, right? There will be 32 electrons, valence electrons, in this structure. You know that carbon will always be your central atom, and you know that the other ones will want to be as far away from each other as possible. Okay, It's very similar to the one we just did beforehand. Okay, know that 2 electrons are in each bond. 1, 2, 3, 4, 5, 6, 7, 8. So you just used 8 of your electrons. 32 minus 8. That whatever that is, 32 minus 8, your 24, that will be the other electrons that you need to use, because you know that the 32 will have to add up. So you have this 24. And what do we also know? We know that each atom wants to be happy. We can check this carbon, right? It has 1, 2, 3, 4, 5, 6, 7, 8. It has 8 valence electrons. And what did I say about 8? 8 is a number that it really likes to be at. But these chlorines, they only have 2 next to them. They're not happy at all. So what we need to do, we need to add electrons to them so that they have their octet. That's what it's called, their octet. They're 8 electrons. So 1, 2, 3, 4, 5, 6. So that it adds up to 1, 2, 3, 4, 5, 6, 7, 8. This one's happy now. Okay, so we use 1, 2, 3, 4, 5, 6. We can do the same thing. Another 6 on here. And another 6 on here. And another 6 on here. What does that add up to? 6 times 4? 24. You just use another 24 electrons and you're done. This is the Lewis structure for CCl4. And if you can't understand this little line right there, it's basically just saying that this is 32. We used 8 electrons from the bonds to get 24 electrons left, and then we used the rest of the 24. Sorry, I know that my calculations can be a little messy sometimes, but everything other than that, there are harder examples from this, but that's all we will cover in this video. Anyways, that's it for this video on Lewis structures and bonds. Remember, it only gets better from here. Bye, guys.